Welcome everybody to the new version of Civil Designer 8.3 Stormwater. In this section, we'll look at the new Greenfield runoff estimation, which is now included in Civil Designer. For this demonstration, I'm going to have the projection settings set to the system of OSGB. Within the Greenfield's runoff estimation, Civil Designer will cover both the IH124 and the FEH methods. The user can change between any of the methods during any stage of the design to recalculate and regenerate the reports. In this video, we'll cover the FEH method. When populating the data, the user can choose between doing this manually or automatically, finding and retrieving the required data. We'll populate the data automatically. Right away, Civil Designer will load up the map and navigate to the location in the world based on our DTM survey information within the project. An internet connection is required to load the physical map, which serves only as a visual to see the location from which the data can be retrieved from the database. The map is blue, which indicates that the area is inside a predefined polygon region, which is used to automate the calculations. In this example, we'll move the location point to a new location. This will show that Civil Designer will store the new location, which will be used in the Greenfields demonstration and later on in the video generating a storm shapefile from the same location. Now that we've accepted this location, we are informed that there are three closest weather stations. We can select one of the three or the weighted average of the three. Weighted being based on the distance from each station, making a closer station's data more influential. While this data is only for the FEH, this dialog will show even when you're using the IH124, allowing you to change between the two methods at any stage of the design, as stated earlier. Civil Designer can now retrieve the hydrological region, the standard average annual rainfall, the host classes being the hydrology of the soil type, and the BIF being the base flow index per host for the location of the project. The 1, 30 and 100-year runoff rates per hectare and the Greenfield's runoff rate are automatically calculated using the retrieved data and the user entered data such as areas. We can now compare the difference in results using the two methods. Choose the method and click on the next button. Calculating the attenuation storage required. In this section of the wizard, we will automate the required attenuation storage. All the grayed out items are values directly calculated from the previously acquired graph or were set in the previous page. Here you can see the development area shown as 10 hectares and the M5 60 rainfall shown as 20 and the M60 minute to the M5 2-day have all been set in the previous page. The climate change factor is adjustable. This can be changed based on which guidelines or authority the user is adhering to. The FEH rainfall factors, which are the scale factors to adjust the output values, are pulled from the map. The storage volumes step-for-step results are shown, with the final estimated attenuation storage in meters cubed is shown for the 1, 30 and 100-year return events. Calculating the long-term storage required, most of the data has been populated from the previous pages. You'll note the proportion of paved area draining to the network alpha is currently hard set to 1. This is required by all the formulas. However, this can be made editable by checking the set alpha as editable. The proportion of pervious area draining to the network beta and the runoff factor for contributing paved areas RF are both user-defined values. As shown here, the results for the long-term storage volume is expressed in cubic meters per hectare. Calculating the treatment storage required. The last window will be for the treatment storage volume required. There are no inputs required by the designer, as all the required inputs have already been input on earlier sections of this wizard. The results for the long-term storage volume in cubic meters per hectare are shown here in the center of the dialog. Printout of the report. We'll print to PDF and review the results. Here you can see all the input and calculated data presented in the PDF ready to be added to your design report. We'll now quickly look at the new additions added to the storm control panel. When working with the Greenfield's runoff calculation, method IH124, also known as the FRS, the creation of the storm shapefile has become easier. Click on the Browse button. Civil Designer will load up the map at the previously chosen location, or the center of the project if it has not yet been opened within the project drawing before. Click OK and load the storm data into the storm control panel. Civil Designer will now retrieve the hydrological region, the annual rainfall, the host class, the BFI host for the location of the project. We'll now look at the Soakaway design. The Soakaway design holds a number of variables for the design to be correct. First, you need to calculate the infiltration rate and the ratio, which are fixed variables. Infiltration rate. If the soil infiltration rate is already known, set the calculation mode to manual and enter the value at the bottom of the dialog. If the soil infiltration rates are unknown, input the trial dimensions first, then input in or right-click and import the values from CSV into the trial pit spreadsheet on the left-hand side of the dialog. Civil Designer will now take the difference between the time to empty at 25 and 75%. From that, the longest outflow time, which results in the slowest draining trial pit, will be used. Looking at the ratio, Civil Designer can again choose between the manual and the automatic mode. Should the automatic be chosen, a map will be displayed at the mean location of the project. We'll now accept this location. The easting, northing, and country name have been extracted out of the map database and into your project. The calculation requires a ratio of 60-minute to 2-day rainfall of the 10-year return period. In order to obtain the M5D values, are scaled using the growth factor to translate them to the required M10D values for the rain event. The ratio and growth factor value is determined from the selected location on the map. Variables to calculate. Populate the remaining outstanding required information. See this as a checklist for the outstanding information required. And set the variables to calculate, which can be any of the following: the upstream area for the soakaway to cater for, the free volume due to the backfill percentage, the internal diameter of a concrete ring, the effective storage depth, or the length and width of the soakaway. Once the variable to calculate has been selected, a Civil Designer will grey out the item below. Now we'll look at the given area's rainfall duration period from the 5-minute to 12-hour. The stormwater retention required for those periods are calculated. The peak required storage is reached at the center of the storm duration. From that, the required width is calculated, and the time to drain that water out of the soakaway is calculated from the calculated widths. The maximum width and the time is then found and placed in the outputs above. In this example, the width of the soakaway needs to be at least 1.3 meters. If we change the calculation to runoff area and we keep the width at 1 meter, then the soakaway will cater for 77 square meters of the catchment area. As an experiment, we'll change the upstream area to be determined. We'll set the width to 1.3 and notice that the area calculated is 100 square meters. The print output. We will print to PDF and review the results. Here you can see that all the data, both the input and calculated, are presented in the PDF, ready to be added to your design report.